All right, good morning, and welcome to the Communication and Signal Processing Seminar. Yes, and welcome to 2021. Hopefully this is a much better year and we can transition at some point to in-person seminars. But in the meanwhile, we still stick with the online version. So I should start by saying I really like to thank the Shelley Felcam and now Catherine Godwin, who are helping with arranging the seminars. Without their help, nothing will run. And also should thank the sponsors, KLA, as well as the research areas, NCIS and SIPML. So today I'm delighted to have Laurent Massoulié speak. So I just should have a preview as well. Since we are all online and people are not traveling, I thought we could get people from across the world, experts to come and talk. And Laurent is one such expert. And given his time zone, if we'd have this early in the morning. And we have a few more seminars like this early in the morning coming up in the early part of this semester. After that, we go back to the usual time of Thursday. So Laurent is currently research director at Inria. He's the head of the Microsoft Research and Inria Joint Centre. He's also a professor of applied mathematics in the Center of Ecole Polytechnique. He's based out of Paris in France. His research interests are very broad. They are in machine learning, probabilistic modeling, and algorithms for networks. He's held research scientist positions at various companies, France Telecom, Microsoft Research on its own earlier. This was mostly in Cambridge, then Thomson-Technicolor, where he headed the Paris Research Lab. And he has got several research awards, and he's very well recognized in the community. And some of the paper awards are the IEEE INFOCOM 1999 Best Paper Award, ACM SIGMETRICS 2005 Best Paper Award, ACM CoNEXT 2007 Best Paper Award, and more recently NeurIPS 2018 Best Paper Award. He was elected the Technicolor Fellow in 2011 and received the Grand Prix Scientifique of the Duca Foundation, delivered by the French Academy of Sciences in 2017. He's also the fellow of the Prairie Institute. So with that, I'll let Laurent take the floor. So yes, in terms of questions and stuff, please either ask or put your hand up and I will monitor the chat. And I will be the discussant after Laurent finishes, and then we can open up for more questions. Please, Laurent, go ahead. Yeah.
All right. Thank you, Vijay, for the very kind introduction and for the invitation. So today my topic is from tree matching to graph alignment. And this is based on joint work with my PhD student, Luca Ganasali, who also presented the work at the COLT conference online last year. All right, so to give you a bit of context, let me start by reminding you what the graph isomorphism problem is. So by definition, given two graphs, G and G prime, the existence of a graph isomorphism is the existence of a bijection F between the nodes of one graph and the nodes of the other graph, such that this mapping F does preserve adjacency. So ij is an edge in the first graph if and only if f of I, f of j is an edge in the second graph. So that's a famous problem because it's an odd beast. It is in NP. However, it's conjectured to be neither a polynomial time solvable nor to be an NP complete problem. Okay, so that's a famous graph problem. And what we are going to consider in this talk is graph alignment, which is in some sense a relaxed version of the graph isomorphism problem, which can be described as follows. We are looking now for bijection again from the vertices in the first graph to the vertices in the second graph, but we are now asking that this bijection preserves most edges. So the picture I have here is more or less the same as the previous one, except that there is a missing edge on the second graph. So this is deemed a decent alignment, despite the fact that it is not an isomorphism. Formally, what we mean by an alignment, so the ideal alignment would be the function f that minimizes the sum of pairs ij of vertices in the starting graph G, such that we don't map ij as connectivity property, that is being an edge or not being an edge in G, to the same property in G prime. So that's the minimization I've just highlighted. And as such, it's a specific, a special case of the well-known quadratic assignment problem, which can be phrased as follows: if we call A the adjacency matrix of the first graph G, and A prime the adjacency matrix of the second graph G prime, then the problem I've just written, this minimization problem, is also the problem of finding permutation with matrix pi associated to it, such that we maximize the trace of this quadratic function in the permutation matrix pi. And so this particular problem, the quadratic assignment problem, which is this maximization when A and A prime could be arbitrary square matrices, turns out to be an NP-hard problem. Okay, so that's the problem that we will be concerned with. And before I describe a specific generative probabilistic model for which we are going to study the graph alignment issue, let me give you quickly a few applications that this graph alignment problem has. So first application is that of de-anonymization of users' identities in social network data. And so that's supposedly illustrated by the picture on the screen. So if you have a graph capturing relationships between users of one social network for which you know their identities, and you can somehow align this to the graph of another social network for which user identities are hidden, then maybe you can de-anonymize those identities if you are able to align properly the two graphs. Another example of application that comes from biology is if you consider graphs of interactions between proteins in the cell chemistry for one species, A, and a similar kind of graph for interaction of proteins in the cell chemistry of another species, B, then suppose you know quite well the biology of the first species. Maybe this is the Ecole bacteria that has been studied to death, and you know exactly the role of the particular proteins for species A. Then this alignment can help you guess the role of proteins in the biology of species B. So I'll give a couple more examples of applications, and then we can forget about applications. So in the same spirit as the first two applications, people in medical imaging have been using alignments in the following manner. Imagine you have captured data of the 3D shape of, say, a heart using a MRI. Now you can construct a mesh of the surface of the heart of a patient using this MRI data. And that gives you a graph, this mesh. And suppose you can align this graph with the mesh of the heart of a reference patient, for which you have annotated very carefully the distinct parts of that mesh into ventricles and whatnot, so all the constituting parts. So now alignment allows you to lift the annotations from one graph to the other one, and so you know how to cluster the mesh of the heart of your new patient based on the reference heart model. Okay, final example I wanted to mention is assume your two graphs are graphs where the nodes are words in languages and the edges represent proximity, so maybe a semantic proximity of distinct words within the language. Now, if you can build a graph that maps the semantic structure in one language to that of the other one, then maybe there is hope that this alignment will give you some kind of a two-way bilingual dictionary to go back and forth between the two languages. So you can think of quite a few applications of that problem. And there are so many that we can forget about all of them now and address the problem for its own sake. Okay, so we will look at it, as I mentioned, in the context of graphs that are generated by a specific generative model, which will allow us to do some analysis and get some detailed understanding of the properties of various schemes for the alignment problem. So I guess all of you know about the famous Erdős-Rényi random graph, GNP, where n is the number of vertices and p is the probability of presence of an edge between any pair of nodes. And so in the Erdős-Rényi random graph, edges are placed independently of one another between any pair of nodes. And so that's Erdős on the left and Rényi on the right, if I'm not mistaken, for the pictures. And so we are going to consider the following two graph version of the Erdős-Rényi graph. It's called the correlated Erdős-Rényi graph model. So, and it's usually denoted as ERC with three parameters this time. N is going to be the number of vertices. P is going to be the probability of presence of an edge between any two nodes in both our graphs G1, G2. And S is some form of a correlation parameter between the two graphs. So how do we build that? Well, we start with a master graph. That's an Erdős-Rényi graph with n nodes and edge probability P over S. And then we downsample the edges of that graph. So we keep them with probability S. We do that once, and that gives us a first graph G1 with it's Erdős-Rényi again, and it's with parameters N and P. And we downsample the master graph G0 once more, and that gives us yet another Erdős-Rényi graph G'2. So they share the initial master graph, but the downsampling is done twice independently each time. Okay, and so as a result, I mean, if you want to detail the statistics for this pair of graphs G1, G'2, then an edge ij is in both of the graphs with a probability p times s. Whereas an edge is in G1 and not in G'2 with probability P 1 minus S. So we have fully described the model, and what we want to find actually is the following. So we assume we shuffle the identities of the nodes, and so from G'2 we form G2 by picking uniformly at random permutation of the n node labels. And so what we get to see is on the one hand the graph G1, and on the other hand the graph G2, which is G'2 with shuffled node labels. All right, any questions on the model? If not, so
no. Yeah. No, I'm good with the model. Anyone else, any questions?
Okay, the model is clear then.
Yeah.
Okay, so the benefit of considering this generative model is that we can really precisely define what it means to succeed at realigning the graph and the two graphs. It would mean, based on G1, G2, to recover the permutation that has been used to shuffle the labels of the second graph. So let me mention a couple of existing works on this problem. There's a very nice work by Kulina and Kavash in 2016, which characterizes the threshold on the parameters of the model for the possibility to recover exactly the permutation sigma. And so they showed that if the product NPS of the three parameters is log n plus something going to infinity, then as n becomes large, there is an algorithm. It's not polynomial time, but it can be described, which succeeds with high probability at recovering the unknown permutation sigma. So that's for the information theoretic threshold. It is a threshold because if NPS is not log n plus omega of 1, then you cannot succeed with high probability at recovering the permutation sigma. So people have also looked at feasibility of recovering this permutation in polynomial time rather than information theoretically. And there's a paper in 2018 by Jen Ding, Jiaming Su, and co-authors. And they show that if the average degree in your two Erdős-Rényi random graphs, NP, is some power of log n at least, and if the difference between 1 and the correlation coefficient S is little o of negative power of log n, then you can do exact recovery of this permutation in poly time. Okay, so as a result of these previous works, we know that we will be able to recover, even without the constraint of polytime, the permutation only if the average degree in the graphs we are looking at is at least logarithmic in the number of nodes.
So Laurent, a quick question. In the information theoretically feasible regime, this is the connectivity regime, right?
Yes, it is the connectivity regime.
And so does that play a role in why it's feasible, or is there some other factor that makes it work well?
Well, actually, it is needed that you have connectivity, and you have connectivity in an Erdős-Rényi graph with parameters n and p times s. And it turns out that there is a notion of an intersection graph between G1 and G prime 2, which is precisely an Erdős-Rényi graph with parameters n and p times s. So this is precisely connectivity regime for the intersection graph. So okay, that's needed. This is indeed critical.
All right, thank you.
So what we are after is properties or algorithms that would do something useful in a sparser regime. We are interested in graphs with average degree order 1, and so we know that exact recovery is doomed. It cannot be done. But our point is that maybe this is too much to ask, and there may be relaxed objectives that are still very useful to achieve, even though exact recovery cannot be done. So our relaxed objective that we will go for is to find some permutation of the node labels such that we recover non-vanishing fraction of the correct permutation. So we introduce this notion of an overlap for our permutation that we estimate from the data, sigma hat, which is the fraction of node labels we recover correctly of mappings of the nodes in G that we correctly infer. And we are actually going to ask a bit more. We'll ask that the fraction of mismatches is going to be negligible. So that is something we would also like. That would be okay. Right. So that's our objective. And what I want to describe today is our result in reaching that objective. So that's the theorem that that you see on the screen now. Okay. So we look, as I said, at sparse graphs regime where the average degree is lambda, a fixed scala. And what we will see is that for lambda between 1 and some constant, there is a critical value for the correlation parameter S. So there's this S star that depends on lambda. And if our correlation parameter is between this critical value S star and 1, then an algorithm I'm going to describe in a while, the neighborhood tree matching algorithm, does return a permutation in polynomial time that achieves a positive overlap with high probability, and that achieves also a fraction of mismatches that is negligible with a high probability. So I drew a phase diagram for the alignment problem on that slide. So the x-axis is the average degree in our graphs. Oh, okay. Let me go back to the slides. Sorry about that. Nearly there. Okay. So x-axis is the average degree in the graph. Y-axis is the correlation parameter. And so if the average degree is less than 1, we have individual graphs, G1 and G2, which have no giant component. They are collections of tiny connected components. And that's a situation where we expect that nothing can be done. And so our theorem describes that we can be successful in this green triangle that I've just highlighted. And you should contrast this with the two prior results that I was describing. So the blue area here, that would be Kulina and Kiavash. This is the IT information theoretic feasibility. That's for lambda times S that is at least log n. Whereas the other green area, this is the Ding and Su et al. Result. So you see that we are able to say something about the order 1 average degree case and polytime as well. Okay, and it's not clear what's going on in this white area here. All right.
So just a quick question, Laurent, before. So even in the region where your results, the green is, do you know how it, suppose I only want, so you said you're getting asymptotically, you're getting the entire, the fractional alignment is 1. But if I only wanted 70% alignment,
no. I'm not getting 100% asymptotically. I'm getting X%, and
X%. Okay.
Yes,
right.
yes. X will depend on lambda. It will depend on S. And for instance, it's intuitively clear that you cannot correctly recover the alignment for isolated nodes in your two graphs. So you know that you're doomed at least on a non-vanishing fraction of nodes. So that's right. So yes, so
yeah, because you're below the connector, you're below the connectivity regime. So yes, you will have isolated nodes which you can.
yes. And
No,
so
thank you for the clarification.
okay, and so one thing maybe that I said that was not totally correct is that we are not going to produce a permutation. We are going to produce a matching of the nodes. So we are going to claim that for some nodes we know who they should be aligned with, and for the other ones we shall not say anything. So this is why we can ensure that we don't have a sizable fraction of mismatches, because otherwise that could not be achieved.
Well, thank you.
Okay, so I'll tell you about tree matching weights, which is the building block for main building block for our algorithm, before describing the scheme itself, and then detail a little bit some of the arguments that we need to develop in order to arrive at the result. Okay. So we are going to make use of the following notion of a tree matching weight. So if you have two trees, T and T prime, with a distinguished node that is the root of the tree, row of T and row of T prime, then we consider subtrees T second that are subtrees of both T and T prime, and we measure the size of T second by the number of nodes that they have at distance D from the root. And so, for instance, here highlighted in red, you have a subtree of both T and T prime on the picture, which has 7 nodes at distance 3 from the root. And so our tree matching weight, WD of T and T prime, that's defined as the largest number of distance D nodes from the root that we have in a subtree common to T and T prime. So you can see that this is related to some kind of metric between rooted trees, because if the two rooted trees had the same number of leaf nodes at distance D, and if the weight that we obtain is exactly that that number of leaf nodes at distance D, then it means that the two trees are isomorphic. So the good thing about this tree weight is that it can be computed recursively, so that given two trees with a number of given number of nodes, computation of their matching weight is going to be a polynomial time, and that's something we can see from the recursive formula we have for computing this. We can consider neighbors of the root nodes. So that would be neighbors I of the root in node T, neighbors U of the root in T prime. And if we know the matching weight of the trees that are rerouted at these nodes here of depth D-1, then by summing over pairs IU in a matching of neighbors of the root in T and neighbors of the root in T prime, we do get our matching weight. Okay, so that's why it's polytime computable. So that's good. We can use that in a scheme. And so the first scheme that we considered, which gives the idea of what is going to work, even though we will have to fix it to get to the result, is the following. So we would say vertex I in G1 ought to be matched to a vertex U in G2, provided their neighborhoods in both graphs are trees up to depth, up to distance D. So we have T1, T2 as the trees, and we would want to consider them as a match in our alignment if the corresponding weight at depth D is above some threshold. So this does not quite work because of the following source of false positives for matches. We will see that it does succeed at correctly identifying a true aligned pair, but it would also be confounded by counting as correct aligned pairs, pairs that actually are neighbors in the original graph. So that's what I'm trying to illustrate on the picture here. So imagine before you shuffle the nodes, you have nodes I and U, which are nearby in graph in the master graph G node, say. Then they may share rather dense subtree in their neighborhood, both in G1 and in G2. And that's the tree that I'm depicting here in red and green edges. So that would be a false positive for this scheme. So we go to a slightly more involved scheme, but the key idea was already present in the first attempt. So the more involved version is somehow introducing a trick to get rid of those false positives. And the trick is as follows. We'll actually say that we want to match two nodes I and U of both graphs if the following holds. For I, we can find two neighbors in G1, J, J prime, and for U, we can find two neighbors in G2, V, V prime, such that the dangling trees from I, from edge GI in G1 and the dangling tree from edge VU in G2 have a high weight. That's what I write here. And similarly for the other pair of neighbors, so the dangling tree from G prime and the dangling tree from V prime in the two distinct graphs have a high matching weight. Okay, so that's the scheme that we are going to use to decide that we want to match IU. And so the theorem in a more precise form says that for logarithmic D and for a threshold in our selection of pairs IU that is order lambda S to the D, then with high probability, the pairs that we create take a non-vanishing fraction of the true aligned pairs, so I sigma I for the unknown permutation sigma, and the fraction of pairs we create that are not aligned pairs is little of 1. Okay, so that's the if you like the more precise version of what we actually achieve. And that's the algorithm for which we can prove something.
And as you were saying, there are nodes that you don't match at all. You just leave them.
Yes, exactly. Otherwise, we could not achieve non-vanishing correct overlap and vanishing rate of mismatch because of, say, for instance, the isolated nodes. Okay, so I'll try to give a feel for some of the arguments that may be of independent interest in proving those results before showing a couple of simulations and concluding. So one of the important arguments is that we can characterize somehow the matching weight and its behavior when we have two nodes that are far apart in the graph, and that is going to be in fact close to the matching weight behavior if we had two random trees, T prime, that are Galton-Watson branching trees with a number of children for each node that has a Poisson distribution with parameter lambda. And so one of the key lemmas to get our result is the following. We know that for two independent Galton-Watson random trees, when we consider their matching weights at depth d, then it's going to be growing like something that is at most gamma to the d, where gamma is small compared to lambda times s, where lambda times s is a key parameter for us. And so that's something that we show by induction on D, showing a bound for some stochastic ordering on this matching number for two independent trees. So that's I won't say more, but that's a key step. So an argument we need to make now is about the local structure of our graphs G1, G2. So it is something classical in the random graph literature, that in a sparse Erdős-Renyi random graph, then the local neighborhood of one node in the graph looks like a Poisson Galton-Watson branching process. And all right, so now if we consider the pair of graphs before we shuffle the labels of the second graph, then we can look at the local structure of this beast and extending the classical result on the local structure of a single Erdős-Renyi graph, then we would be able to show that in the union of these two graphs, the local neighborhood of a node behaves like a three-type branching process with skew-table offspring distribution. And so the three types would be double edges on the one hand, edges that appear both in G1 and G prime 2, and then monochromatic edges, so orange edges in G1 and green edges in G prime 2. And a special case of that is if you focus only on the double edges. So these are the edges in the intersection of the two graphs. Then that does behave like a Galton-Watson branching process with offspring distribution that is Poisson with parameter lambda s. And so so now, I mean, the key idea is that if you have a correct match and you look at the matching weight of the tree neighborhood of the nodes of the correct match, U in G1, I in G2, then by this local structure property, we know that they both contain a subtree that is the tree in the intersection graph. And so this subtree behaves like branching Poisson process with a parameter lambda s. And so by well-known results on the behavior of branching processes, we know that the number of descendants at generation D is on the order of lambda s to the D with a positive probability. And in contrast, if we have two nodes that are far apart in the union graph, then the neighborhood in one graph and the neighborhood in the other graph, they look like independent Galton-Watson branching processes with Poisson offspring with a parameter lambda. And so by the analysis that we can do for the case of two independent branching processes, we know that the weight in that case behaves like at most gamma to the D, where gamma is less than lambda s. So that's the crux of the argument. We can then set a threshold tau, which is constant times lambda s to the d, and we will retain a positive fraction of the correct matches because of that. We will, however, cross out pairs that correspond to faraway nodes. And the rest of the argument that gets technical is in making sure that we have no false positives, or at least a vanishing fraction of false positives. And this is where the elaboration of this scheme using two dangling trees rather than just directly the neighborhood of the nodes comes into play. And so that's part of the paper that is perhaps not the easiest to read, how to discard the other cases where a false positive might have occurred. All right, so I will just show a couple of pictures before concluding. We have not yet run large-scale experiments with that scheme. Right now, its interest is more of a theoretical nature, but let's see nevertheless an illustration of its properties. So here, this is for varying number of vertices on the x-axis. So and I think this is for a correlation parameter S taken equal to 1, which means that we were actually dealing with isomorphic graphs, G1 and G2. There was the same master graph, G naught equal to G1, and G2 is just a shuffling of G naught. And we do see that we managed to match a fraction of nodes that is at least 20% correctly, and we don't get any or a negligible, at least, fraction of false positives in our matches. Okay, so now let's have a second plot illustrating the impact of the correlation parameter, and that's not very large scale, but 150 nodes in both our graphs. And so we do see that the fraction of false positives stays low, and the fraction of correct matches does increase as we let the correlation parameter S approach 1. Okay, so conclusions now. What I like about this problem is that it has those various many applications. So I think it's there are sufficiently many interesting applications that it's worth studying this problem on its own. And so we have started the study of a partial alignment, and with this NTMA algorithm, we have showed that it is possible to succeed at partial alignment for sparse graphs, correlation parameters that are bounded away from 1. Sorry. So that's also a challenging thing, and we do that in polytime. So that's also one feature that is quite important. But there's much more that we would like to do and that we don't understand yet. So if you recall the phase diagram I was showing, one would imagine that there exist boundaries in this phase diagram in terms of the parameters lambda, the average degree, and S, the correlation parameter, that delineate when we have IT feasibility for partial alignment. We don't know the boundary of for that, and it's not clear either whether the boundary between polytime feasibility and impossibility of polytime partial alignment is the same as the boundary for the information theoretic phase transition, or as in other problems, such as community detection, would there exist an intermediate range where it is IT possible to do a partial alignment, whereas it's not possible within that region to do it in a polytime? Okay, so the delineation of the IT feasibility region is not done yet in the sparse case. We have some partial results with a student, former student of mine, Georgina Hall, last year, but there's still a lot to be done. And final point, the scheme we have becomes more and more expensive as we look at denser and denser graphs. So it's well suited to align very sparse graphs, but it would be interesting to come up with schemes that work for denser graphs. And it deals in a not very satisfactorily manner with cycles, because it just ignores nodes whose neighborhoods contain cycles, and so that's obviously discarding potentially useful information. And so here as well, there's scope for coming up with better solutions. All right, so that's it, and I'm happy to take questions.
Well, thank you, Laurent. So I'm going to actually, if you can stop sharing, I'm going to share my screen. So I'll just have a short, some questions and discussion, and then I'll open it up for broader questions. Oh, okay, well, I'll just do this. Okay. So thank you again for a very nice talk. I very much enjoyed it. So I had to, I'm just going to summarize it briefly and then sort of talk about my questions. So the high level overview of the theory is this: perfect matching is information theoretically impossible for sparse graphs, but approximate matching is possible, at least in some regime, even with a polynomial time algorithm. The algorithm presented works by comparing and matching rooted trees. The base algorithm needs correction as there's noise amplification in some sense, and the correlation is done by matching subtrees rooted at children of the root node. That would be my summary of what was presented. So the questions I had were, I'm going to sort of read, we can go. So at the high level, you're picking a motif of some kind, and in this case, you're a tree, and for approximate matching, and it works. This motif works because you're looking at sparse random graph families, especially the ER graphs, which is locally tree-like. And as a part of the analysis, you're coupling to a Galton-Watson branching process. So, so the question is, would this type of analysis or methodology work for larger graph families, such as they come from, I'm still sticking to random graphs here, the configuration model or Chung-Lu graphs, which also yield locally tree-like graphs. And in particular, my question comes from the fact that now, if you have the Poisson lambda Galton-Watson branching process, the distribution of the degree distribution, the child distributions is the same as you go down the tree, whereas in these other graphs, you end up getting size-biased distributions. So you may have, you may need additional corrections to the sort of way you're comparing things, or not, I don't know. So, so that was one question that I had.
Okay. And do you want me to try and?
Yeah, if you want to answer that, then I can go to the next question after that, because there was a slightly different question. So maybe that's.
Yeah. So I think it's a very interesting suggestion to look at other random graph models, which would produce other statistics for the trees describing the neighborhoods. Actually, even for the Galton-Watson branching process with Poisson offspring, we have difficulties in going beyond what we already managed to do. So I guess it is only going to get harder. But so, for instance, we have this restriction on the range of average degrees over which we can claim result. So lambda between 1 and lambda naught. And we believe this is a technical restriction, but the proof does not carry over to arbitrarily large lambda. So it's a very good suggestion. I don't know how challenging that will be mathematically.
No, thank you. So then the next question you sort of answered towards the end is, how would you generalize your algorithm to other graph families, say that have smaller cycles? I mean, you're locally tree-like, so the cycles are about log n. And then what sort of correction would apply? In particular, I'm thinking of graphs like k-regular random graphs, which have small girth, but only a few small cycles. Most of the cycles are very large. And here, in particular, here also connectivity will hold if k is at least 3. So it has lots of nice properties that make the results from information theoretic feasibility and various things carry through. But still, there are cycles. Are there other motives you should consider, and so on and so forth, is sort of the related question here.
Right. Yes. So, I mean, ideally, we would like to be able to match neighborhoods and live, and if we have grid-like structure on some of the neighborhoods. So one very tough thing is the random regular model that you describe, because then the neighborhood, the typical neighborhood is a regular tree with a number of offspring that's 1 degree minus 1, and so you would have a match with everyone. You see.
Yes,
so
that's right. Yeah.
That's a case where you are at a loss. So it's actually a very challenging situation, finding an alignment in the case of random regular graphs.
Because there's no way to distinguish things. That's correct, right?
Yes, so essentially our scheme is local, and it leverages the fact that you have some fluctuations in the neighborhood of nodes that you can relate to fluctuations in the other graph you're trying to align to. If you enforce this regularity constraint, and you have for most of the nodes a tree-like neighborhood, then you're doomed with local approaches. So you would need some global information, and so you need to rethink the scheme, basically.
Okay, no, thank you. No, that makes a lot of sense. Yeah, so that's why I'm asking, would other motives be relevant to use as opposed to a tree? Yeah.
So I think this does make sense, and maybe we should also think of combining local motif matching with a global mechanism. Takes into account the global properties of the graph that is not based just on neighborhoods.
So the third question, I have a fourth question which I didn't write down, which I will mention at the end. So how would one generalize this type of scheme? In some sense, it's building on the fact that your the subtrees of the neighbors are independent. So in a way, if you're making, if they're aligned, they have then it's aligned with very high probability if you're very close. If otherwise they're going to be very far off. I mean, it'll be the probability will be very low. What happens if you sort of have to look at graphs? And there are examples of graphs, actually some prior work of mine with the student. How would you generalize to graphs which in the asymptotic limit? I mean, this is still in the locally tree-like regime, where the branching process you consider has interdependent child distributions.
I don't know. I mean, I'm curious to learn about the models you developed, which lead to this interdependency.
So that graph had some sort of, it needed some sort of coupling between nodes when they're forming, some sort of agreement, bilateral agreement. So I can send you that paper. But
okay.
So the last question, in a way, is you sort of mentioned it in the paper, but maybe it's good to bring out here is, so you could run your algorithm, you produce some sort of you get a matching, a partial matching, certain, it is right to the extent that the results are. And then you could use a spectral algorithm or something else to then, as a bootstrap, to then say, okay, can I match a little bit further? Do you know how far that would get to? Is there any, I mean, I know there are results. I think Shrikant had some earlier paper. I mean, I don't know if it was a paper published or not, to the master's student, where they were trying to use, if you had some partial side information and then you ran one of these algorithms, you could get substantial improvements.
Right. So the seeded matching problem that would lead to, right? So you
yes,
could
yeah.
use something like what we do to produce a set of seeds, and then do either spectral or otherwise, but enforcing this matching of the seeds.
Yes.
Yes. So indeed, we thought this might be a good use, that one should not stop at the matches produced by schemes like the one I've described, but improve upon that. I have not thought about it more than that. I just know that the early papers on the topic by Matthias Grossglauser and colleagues of his at EPFL were focusing on seeded matching. And so, so one thing I can mention is that they looked at what they called percolation schemes, where you would, match two nodes if they have a number of neighbors that are already matched within the seeds, and that would be a new generation of matches, and you could iterate that. And so that's how.
Yeah. So the seeded matchings were like voters in some sense, right? So if they agreed, then you said, okay, many of them agreed, then you said, okay, yeah, I know that the next one should match.
Right? Yes, and so you could propagate that, and that's why they called it percolation based approach. Yes, but I don't know if people have looked at spectral methods with seeds, and maybe this is something fruitful to consider.
Yeah. So thank you for answering all my questions. That's all I had. So I'm going to stop sharing my screen, and then I'll open it up to questions from others.
I have a question. This is Alfred Hero. Really nice talk to all.
Thank you.
I wonder, I have maybe it's a little bit of a follow-up to one of Vijay's questions. I think the first one on extension to other types of models. The Galton-Watson model plays a principal role in your proof of the main result. So I'm wondering if these results could be very easily extended to preferential attachment trees, which by construction satisfy the Galton-Watson process for all subtrees. So this could be a very exciting extension, because these types of preferential attachment trees have been proposed in genetics and in population dynamics for immune system response to viruses and so forth. Matching in that case could be very important in order to discriminate between different host responses to viral infection that could then help develop new types of medicines or new types of treatments. I'm wondering if, first of all, if you've thought of applying this to the kind of a Barabase Yule process, Yule earn type process models, and if not, what your thoughts are.
Okay, well, thank you for the question. I had not thought about that, but it sounds like a very interesting avenue to pursue. And I I guess one thing that also happens in those Barabasi-Albert random graphs is this power law property for the degrees, which in some cases even allows you to infer with some sort of accuracy who might have been the initial node in the construction. So they would lead. I mean, that would be a natural thing to do, to try and find who were the original nodes, and then you could use this as a seeding mechanism.
Yes.
So I think, yes, not only is this an interesting setup to consider, but you may have schemes that are that use the seeding in that particular way, leveraging work on inference of who's Adam, I think was the title of one of those papers.
Yes.
So had not thought about it, but that sounds like a very exciting direction.
Yeah, it would seem to be a natural one, since it's the crux of your proof depends on these Galton-Watson structures, which, if they exist naturally within the tree and all subtrees, then maybe you could get even stronger results.
Right. Yes.
And one thing that this is sort of another question. The theorem you have is very nice, and specifies a regime in this phase space where you can do considerably better at reconstruction in theory. But I didn't see any kind of guarantees on what proportion of the reconstruction can be correct. So in your theorem, you have high probability that your matching produces a positive non-zero result. But is there a way to lower bound that so you could provide a guarantee that I can get at least 25% correct or 50% correct? I know that it's probably very hard to do, but
right. So the thing we can extract from our proof is indeed a lower bound on this fraction, but this would be tiny and probably quite far off the true fraction that we do achieve. But the way I see it is that we should not only be looking for a phase diagram in 2 dimensions with average degree and correlation. We should also add a third axis, which tracks the fraction that we match correctly. And I would imagine there are, in this 3-dimensional space, surfaces that delineate the boundary between IT feasibility or not and polytime feasibility or not of reconstructing fraction X of the matches. So that's of course even harder than, well, somehow this is harder than the problem of reconstructing the boundaries of these regions when you ignore the fraction that you correctly match. But that's how I tend to think of it. But I don't know how to attack it. The identification of these surfaces in a 3-dimensional space. I don't know if I'm making sense, but
yeah, no, it's a hard problem. So I think, but thank you for your responses. It was very, very interesting. Great to talk to you again.
Thanks.
Any other questions from anyone? It's all open to ask. Yeah, please go ahead.
Yeah, I have a quick question. Hey, Laurent, this is Lei here. I enjoyed your talk very much. So I have a question which kind of relate to VJ's and also L's question. So again, it's about extension. So instead of have like the regular ER graph, if we have a multi-type ER graph, which means the nodes have let's say there are 2 type of nodes. They have different degree distributions. So locally, they will still have this tree structure. Can you comment on whether your methods can be extended to this case, or what will be the potential difficulty to extend to this like multi-type ER graph?
So I think this is probably among the various extensions that we have been discussing. So both Vijay and Al, Barabasi Albert, or random regular, or configuration model. I think if we go to multi-type ER graph, sticking to the Poisson statistics for the number of offsprings, is probably the lowest hanging fruit. So I think the techniques we have should be extensible to yield positive results in that case. So yeah, I forgot to mention. So coming back to power law random graphs, perhaps from the Chung Lu model that Vijay mentioned, or Barabasi Albert that Al mentioned, I think one nice question is that the case that you can always align a non-vanishing fraction of those vertices, even if the average degree is small, just as epidemics may have massive outbreaks in those graphs, even if the average degree is small, because of the existence of a core that is easier to align. So
I see. Thanks. So I have another quick question about that. So if we have a multi-type random graph, is there any advantage of doing like both these alignment also together with maybe node type detection? So on the graph, if we had somehow some way find out which these nodes are more likely to be type 1 or type 2, maybe it also help the alignment, right? So because we are interesting, I mean, certainly like nodes with same type should be aligned together. Like the nodes are different type, you should not align them.
Yeah, I think that makes a lot of sense, and this is actually aligned with some of the applications I was mentioning. So we in the applications to medical imaging, one is indeed interested in clustering the points of a mesh, say of a hard surface. So that's a case where you're interested in the clustering of the nodes. So if you have a couple of graphs that have both some common cluster structure and that are somewhat aligned, then by using the two graphs, then you're probably going to be better at both tasks, at aligning and at clustering, than if you were considering just one graph for clustering, or the two graphs without the cluster structure for aligning. Right. So
great. Thanks a lot.
This may make sense both from a theoretical standpoint and a application standpoint.
Right.
So, I mean, if I may read your question, are you asking of things like, if you take the planted clique problem, if there are two cliques planted there, can you, in the two graphs, can you actually do better than what can be done in one graph in some sense, or very high level?
Yeah, something like that, right? So you have two graphs mixed together, then you want to match, I mean, do the alignment. But there may be a way to distinguish the type of the nodes, which could help in the alignment as well. As Laurent mentioned, like these two kind of coupled, right? Alignment could also help the clustering, and the clustering may also help the alignment.
But I guess in the model, what you would have is in a real model, you'll also have noise in which the labels are assigned, so that there is some.
There's no label. There's no label. Like it's a graph you get, right?
No,
But
no.
you know.
Oh, you
yeah,
don't get the type as well.
You
Okay.
don't get a
You
type. You have to like guess the type as well.
Okay. All right.
Yeah,
That
yeah.
would be hard. Yeah. But you know that the connectivity is different for different types. Okay.
Yes, yes. So you know the model, there's two types, and you know they are two different models, and somehow they mix together, but you don't observe the labels.
No, I think this is a question that's well motivated from some of the application scenarios, and theoretically, I think in cases where you have phase transitions, we know we have phase transitions both for clustering and for alignment. Then combining the two should move those phase transition boundaries. So that's
Right.
Cool thing from a theoretical standpoint as well.
Right.
Yeah, no, that's true. No.
Yeah. Thanks.
Thank you. Yeah. Any other questions?
Question.
Yeah. Any other questions from anyone else? If not, we'll let Laurent go. I mean, it's evening for him. I think dinner is coming up sometime.
It's not yet 5 o'clock. It's tea time.
Okay, it's tea time. Sorry.
I just have one thing to ask Laurent. If you see Pierre Brémaud, please tell him hello for me.
Okay, okay.
Do you see him often?
You know, we don't go too often to the office these days.
Yes.
But I saw him a couple of times over the last few months.
Yes.
I will say hi.
Please do. Yes, I haven't seen him in about a year and a half. But, I haven't
Okay.
seen a lot of people in about a year and a half.
Hopefully it will
All right.
change this year.
Yeah.
Yes.
So let me thank Laurent again. Sorry. Yeah. And thank you again for an excellent talk. And I think it was a lot of stimulating discussion after that as well. And I will send you the references.
Yeah, it's a very interesting suggestions you guys made.
Thank you. And have a nice rest of the evening and weekend as well.
Okay, thank
Bye.
you. Have a nice
Thanks,
day.
Laurent.
Bye-bye.
Nice meeting you. Bye.
Bye.